The year was 1917. The Panama Canal would soon be opened. And in America, Charlie Chaplin became the first actor to command $1 million salary. In Chevy Chase, Maryland, Dr. W.P. Haseman listened intently to a new formula developed by young John Clarence Karcher.
The depth is equal to 1/2 of the square root of the velocity squared, multiplied by the time squared, minus the offset distance squared. So, knowing the speed and determining the travel time, we should be able to calculate the depth to the subsurface reflecting formation.
Kirch, I think you've got something.
And indeed he had. 23-year-old John Karcher hooked onto an idea that would forever change the world of petroleum exploration. In 1917, when John Karcher revealed his formula for calculating the depth of subsurface formations, he knew he had developed something very important. His discovery led to a plan for someday using seismic waves to map structures far below the Earth's surface. The oil-producing world would come to know the reflection seismograph as the instrument which fulfilled that plan. The peace which characterized that Sunday afternoon in 1917 did not last long. The United States soon found itself involved in the war which had been raging in Europe for 3 years. Karcher was sent to France by the U.S. Bureau of Standards to help develop direction-finding instruments used to locate German artillery by the shock waves they produced when firing. This seismology was also used to save lives and foil German plans for creating havoc in Paris with fire from their huge artillery. When the German Big Berthas were fired from 75 miles away, they imparted a tremendous downward pressure on the Earth. The energy exerted on the Earth's surface when these huge cannons were fired traveled deep down in the Earth and refracted back to the surface in many places. Crude seismic instruments picked up these signals and alerted the Parisians that a shell was on its way. Because of the similarity of the physical laws involved, Karcher's wartime studies of sound waves helped speed the application of his theory to the business of finding oil. By 1921, the world was enjoying a new peace. The age of the flapper had descended on America. And Doc Karcher was ready to try his hand at scientific oil exploration. He joined Dr. Haseman in a company known as Geological Engineering Company. This venture had a short life, however, as wildcatters stumbled onto the Burbank field in Oklahoma, and the marketplace became flooded with oil. Karcher and Haseman found that their financial backers were no longer interested in developing what they considered to be unnecessary methods. Karcher moved to a job with Western Electric and let the idea of seismology simmer until 1925, when Everett de Gollier of Amerada Petroleum decided to give Karcher an opportunity to prove his seismic reflection theory. These two visionary men met in a second-floor waiting room of Union Station in St. Louis, and Karcher agreed to become vice president and general manager of Geophysical Research Corporation, an exploration subsidiary of Amerada. After 5 years of oil exploration for Amerada, Karcher decided it was time to strike out on his own. Along with Eugene McDermott, a co-worker for several years, Karcher organized Geophysical Service Incorporated. 1930, the year following the stock market crash. With the world's economy in shambles and people standing in bread lines across the country, this appeared to be a bad time for launching a new business venture, especially a questionable business based on an unproven technology. But these two men had the courage to give it a try. They opened offices in Dallas, Texas, and an instrument laboratory in Newark, New Jersey. Soon, this pioneer independent service company, specializing in making reflection seismograph surveys for petroleum companies, was contracting its crews to any oil company which would hire them. Detecting and measuring the arrival times of sound waves reflected from boundaries between geologic formations as a means of discovering potential oil-bearing structures was certainly innovative. It required instruments not yet developed and methodology to be developed in the field on a day-to-day basis. Much of the early equipment was designed by McDermott, but there were problems in getting the equipment built and packaged to withstand the rigors of field use. To solve this problem, Karcher and McDermott recruited a young engineer from Alcoa, J. Eric Johnson, to head GSI's instrument manufacturing laboratory. Model A Ford trucks were outfitted for field use with amplifiers, string galvanometers, cameras, cable, and 35-pound geophones, or jugs as they were called. Among the early achievements of GSI's innovation were the development of a sputter-type shot hole rig, a standard rotary drill rig, an underwater seismic technique, and a continuous series of improvements in both the equipment and methodology of the first basic seismograph work. Although based in Texas, the company quickly proved that state or even national boundaries would not set limits on its activities. In 1931, an exploration crew was sent into Mexico. Other GSI crews were already at work in Oklahoma, West Texas, the Penn York area, and California. The following year, the company began operations in Canada. In 1934, crews went into Venezuela. By 1937, Saudi Arabia, Java, Sumatra, Colombia, and Ecuador were points of operation. By 1938, New Guinea and India were also home to GSI crews. And during the late 30s, GSI launched its first marine survey in Galveston Bay. This first effort employed land techniques, but paved the way for effective offshore operations in the Persian Gulf. Karcher's increasing interest in oil production soon brought GSI into competition with many of its oil company clients. In 1939, a move was made to separate GSI's oil production business from its seismic exploration operations. As a result, the name was changed to Coronado Corporation, with Karcher as president. The Exploration Service was organized as a subsidiary, Geophysical Service Incorporated, led by Eugene McDermott. In late 1941, Coronado's owners decided to sell the oil production business to a major producer. GSI was not included in this transaction, but was sold to four key men in the organization, J. Eric Johnson, Eugene McDermott, and two men who had been early GSI party chiefs, Cecil H. Green and Dr. H.B. Peacock. The purchase had been made on Saturday, December 6, 1941. The exhilaration of ownership quickly faded as night gave way to morning and the news of Pearl Harbor. Before a single working day had gone by, the new owners faced a crisis. With the world at war, much of the company's field of operation under enemy control, and most of the rest being threatened, things looked bleak indeed for the exploration business. It might have appeared that a foundation had been laid, not for a growth company, but for an industrial fatality. J. Eric Johnson, then company treasurer, had the responsibility for guiding GSI through the difficult war years. Johnson later described the situation as hopeless but not serious. The markets to which GSI would turn were being set in motion in Washington, D.C. The National Defense Research Council was setting up the organizations through which university and industry people were to be pulled together to tackle specific jobs in technology and design for the war effort. GSI had a hidden asset, its long experience in building sophisticated electronic equipment for its own use. This experience and Johnson's frequent trips to Washington led to some engineering and development tasks for the Army Signal Corps and a contract for airborne magnetic submarine detectors for the Navy. During the war years, GSI continued geophysical exploration in the United States, Canada, Mexico, and South America, but on an abbreviated basis because of the war and the demands of the Selective Service System on GSI personnel. The government contracts helped keep GSI afloat during this period, but had even more significance to the company in the long run. Johnson's contacts with the Navy led to the recruitment of a young naval officer, Patrick Haggerty, who was to become the principal innovator and architect of a new phase of company growth. Haggerty and Johnson agreed that GSI should develop electronic equipment manufacturing as a permanent part of its post-war industrial career. Haggerty joined the company in November of 1945. By 1946, he had established a laboratory and manufacturing division. The company then became a supplier of airborne radar and sonar systems for the Navy, the beginning of a multi-million-dollar business. The trend which was set in motion by the hiring of Pat Haggerty continued, and as Johnson assumed the presidency in 1950, military sales were outdistancing those of GSI's exploration services. The name of the company was changed to General Instruments Incorporated, and GSI became a wholly owned subsidiary. In 1952, the name became Texas Instruments Incorporated, with GSI still in the subsidiary status. Johnson was TI's first president, and Haggerty was executive vice president. Under the leadership of these two men, Texas Instruments soon became a leader in adapting new technology to high-risk ventures. This led to soaring growth for the company into one of the industrial giants of the nation. While the post-war period saw rapid expansion in electronics manufacturing and the birth of Texas Instruments as an entity, it was also marked by intensive research in seismology. New recording equipment went into the field for testing in 1946, but more experimentation led to new and better field systems. The 1950s were characterized by research into the automatic processing of seismic data. TI and GSI developed and fielded the first high-fidelity analog seismic magnetic recorder in 1954. This was followed by the SeisMac processor, an analog seismic computer using digital logic in its central processing unit. These units paved the way to numerous new data enhancement techniques and development of new data collection and processing equipment by the end of the decade. GSI launched the first practical application of statistical communications theory to the search for oil early in the 1960s with the introduction of the first digital field system, the Model 9000. This was the result of a cooperative effort by Texas Instruments and GSI with considerable support from two major oil companies. Under the leadership of Fred Busey, TI's Industrial Products Division developed the Texas Instruments Automatic Computer, the first digital computer designed especially for processing seismic data. During the mid-60s, the first fully transistorized digital field system, the TI-10000, was completed, and advanced seismic data programs were put into production use. Dynamite was the original seismic energy source for both land and marine use. The 60s also saw development in the use of non-dynamite seismic energy sources. The DynoSeis system, developed by Sinclair Oil and Gas, now a part of the Atlantic Richfield Company, and the VibroSeis system, developed by Conoco Incorporated, came into increased use in GSI's land operations. These were cost-efficient systems which provided an answer to the environmental problems created by the use of dynamite as a seismic energy source. These new energy sources allowed crews to operate in widely diverse environments, from the streets of Los Angeles to desolate trails in West Texas and Saudi Arabia. The revolutionary changes in land operations were paralleled at sea. The air gun was a product of this revolution. All GSI ships were eventually outfitted with tuned air gun arrays, solving many logistical and supply problems common to explosives, and eliminating the danger to marine life from underwater explosions. Seldom have effects been as far-reaching in the geophysical industry as the innovations of the 1960s, which saw GSI revolutionize the exploration industry with digital seismic technology. Long before the close of the 60s, digital recording and computer processing of field data were practically the standard procedure for the exploration industry. As the 60s came to a close, emphasis at GSI was placed on three-dimensional seismic technology as a means of locating subsurface conditions favorable to hydrocarbon accumulations. 3D affords a much higher degree of interpretation accuracy than is obtainable with previous seismic methods. The applications of 3D technology have been advanced by TI's development of the advanced scientific computer used with GSI-developed software, and the use of remote terminals and intercontinental data links to allow direct data input. By the mid-1970s, research and experimentation brought 3D technology to workable system status for both land and marine processing, once again keeping GSI in the forefront of the industry. Today, through research and engineering, GSI continues to be a trailblazer, developing advanced techniques to provide the most cost-effective exploration services to the petroleum industry. Operating on land and sea, GSI offers both reflection and refraction seismological surveys, plus gravity and magnetics programs. A worldwide network of digital seismic data processing and service centers supports all these areas of petroleum exploration activities. GSI has offices and field operations in more than 20 countries, offering a complete line of geophysical collection services for both commercial and national oil companies. GSI was born with an innovative approach to the search for petroleum. That pioneer spirit continues as we look toward a future filled with more adventures in innovation.